All right, this is the first video in chapter 10. So big picture, what chapter 9 is talking about is, well, we learned what a sequence is, and we learned what a series is, and then the main question was, how can we determine if the series, if this sum of an infinite list of numbers equals some finite number, if it converges to something? And towards the right at the end of chapter 9, we, rather than talking about just a list of numbers, we started talking about, all right, what happens if we add together a bunch of functions, specifically a bunch of polynomials? And we saw a few examples where, for particular ranges of inputs, this sum of functions ended up equaling another function. So what chapter 10 is talking about is reversing this process. We're saying if we start with some function, maybe some function that can't be integrated, how can we sort of rewrite it as a sum of polynomials? How can we figure out what those polynomials should be? And the answer is, well, we want to pay attention to the derivatives. So using what was called a Taylor series, we're going to, if we can find the derivatives, or as in a whole bunch of derivatives of our function, we can use that to come up with a list of polynomials that, when added together, equals that function. So the underlying idea is that we want to mimic a function's behavior in the neighborhood of a certain value. So what that means is matching its first derivative, maybe its second derivative, etc. So we're going to start off with an example. So say we have some function that we're going to call f of x. And this is maybe some sort of messy function. We don't really know how this function works, but we're assuming that we can find its derivatives at certain points at least. So to start off, let's say that we want to find the equation of the line that matches f of x and is tangent to it at point 0. In other words, we want to find the equation of the tangent line at x equals 0. And hopefully this is a question that you have seen before. And the answer really comes from using the derivative. So the thing that we're looking for is the line that goes through the point and matches the slope of our function. So we want the equation of this line. And well, the equation of any line can be written as y equals mx plus b. I'm actually going to switch the order of those, totally inconsequential, but it keeps the pattern that we're going to see a little bit cleaner. Y equals b plus mx. So we want to know the equation for the line that is tangent to our function f of x at x equals 0. All right. And so we can find this by determining, we can get these particular values from the function itself. We're looking for, we want this equation to have the same y-intercept as f of x. In other words, this b should just directly be equal to whatever our function f of x is evaluated at 0. Right. We also want the slope of our line to match the slope of the function at x equals 0. So the slope m should be whatever the derivative of our function is evaluated at 0. All right, so this thing is called the first order or first degree Taylor polynomial. And what this is this is the function that matches the the 0th derivative and the first derivative. In other words, it has the same value and slope as our function in question at the certain points. So in this case, the first degree Taylor polynomial is the equation, or let's actually call it that. We typically call these functions P1, or the first degree is P1. So the first degree Taylor polynomial is f of 0 plus f prime of 0 x. And what I want to point out, so this is a function. It's the function that is the line that's the same as this y equals mx plus b from before. And this polynomial matches its value and its slope to f of x. In other words, if we were to take our polynomial and evaluate it at 0, in other words, we're plugging in 0 into this function, well, we're putting in a 0 in for x. That means that this is just going to be the same thing as our constant term f of 0. In other words, this is saying our polynomial, in this case this line, has the same value, takes on the same value at 0 as our function f of x. Similarly, if we take this function's derivative, so p1 prime evaluated at 0, well, the derivative of this function, remember x is our variable, so this is just a constant. F of 0 is just a constant. When we take the derivative, that goes away. When we take the derivative of whatever this is, if this is 3x, that just becomes a 3. So the derivative evaluated at 0 is f prime of 0. In other words, these equations are saying that our Taylor polynomial matches up, or it mimics the same value and slope as our original function at x equals 0. Okay, so this line is actually going to be a reasonable approximation of what's happening to this function right at x equals 0. Once we get away from it, it's going to be a little bit off. There's some error on either side of it. Well, if we use a slightly more sophisticated model, rather than modeling f of x with a line, what if instead we modeled it with a parabola? We might do a better job of mimicking what's happening to this function sort of in a better way. So in other words, if rather than limiting ourselves to the equation of a line, if instead we take what's called the second degree Taylor polynomial, what we're doing is we're allowing our function to look like a quadratic rather than looking just like a line. So let's try to extrapolate this pattern. Let's say we want our second degree Taylor polynomial to look like f of 0 plus f prime of 0 times x plus f double prime of 0 times x squared. All right, so this is just a guess as to the format for a polynomial here. So we want to check to make sure that these types of things are true, right? So what happens if we take this, if we evaluate this function at 0? Well, the same thing holds. P2 of 0 is what we get when we plug in 0 for x. These second terms go away. This is just f of 0. Cool. On track so far. P2 prime of 0, if we take the derivative of this, P2 prime of x, well, the derivative, the first term is going to go away because there's no x there. The second term, so if we pretend that there are numbers in for this f prime of 0 and f double prime of 0, if this is 3x plus 5x squared, the derivative is 3 plus 5 times 2x, or f of 0 plus 2 f double prime of 0 x. And I want to point out also that the second derivative of this is going to be, well, we just take the derivative again. We get 2 f double prime of 0. So the second derivative evaluated at 0 is f prime of 0. So that's good. However, the second derivative, I might have said second derivative then. The first derivative evaluated at 0 is the first derivative of our function. So those things match up. However, the second derivative looks like twice the second derivative of f of x. All right, so something went wrong. And the issue is that we're off by a factor of 2. So we can actually sort of go back and fix this. And the factor of 2 comes from when we take these derivatives, the exponents come down. So if we account for that, if we say that, all right, rather than f double prime, what if it's f double prime over 2? How does that change things? Well, that's going to mean that when we take its derivative, the 2's are going to cancel. So this 2 is going to go away, which means this 2 goes away, and which means this 2 goes away. So now with this new form, so this is the general form for the second degree Taylor polynomial. Now, if we have some function f of x, and we know it's first, we know it's evaluated at 0, we know its first derivative evaluated at 0, and we know its second derivative evaluated at 0, this equation, sort of this formula, tells us what quadratic, what second degree polynomial matches our function f of x. So if we knew the derivatives of f, this would tell us what the equation for this green parabola should be. Okay, and as you can imagine, if we allow for a cubic, if we allow for a higher degree polynomial, then we can get better and better approximations of f of x. Right. So the question I have for you that you should work on in your groups, if you are choosing to use a model rather than representing in your discussion group the material in this, one thing you could do is walk through what a third degree Taylor polynomial looks like. So we're looking for a very similar pattern, but we want to know, all right, what should this next term be? And yes, the answer is in the book, but try to work it out yourself. We can use a sort of this guess and check approach that I used here for finding the second degree. We want to figure out, all right, how do we adjust what this third term should be? Okay, so after you've done that, if you happen to see a pattern developing, hopefully then you might be able to figure out what the nth degree Taylor polynomial should look like. How does this pattern continue? And I will certainly discuss these in a later video, but I think this is a good opportunity to discuss this in groups. Okay, in the next video, I will work through an example of applying this second degree Taylor polynomial equation in an example.